Welcome to today's episode, where we're diving into the fascinating world of managing distributed transactions. As systems become increasingly complex and interconnected, maintaining consistency and reliability is more important than ever. We'll explore two foundational protocols, two-phase commit, or 2pc, and three-phase commit, known as 3pc. After that, we'll transition to some more advanced strategies, including the Calvin protocol and Google's Spanner. Each of these approaches offers unique solutions to the challenges posed by distributed transactions, and we'll take a closer look at their strengths and weaknesses. Let's kick things off with the two-phase commit protocol, which is a widely adopted method for handling distributed transactions. In 2pc, there's a central coordinator that collects votes from all the participating nodes to determine whether to commit or abort a transaction. This process unfolds in two distinct phases. In the first phase, the coordinator reaches out to each participant, asking them to prepare for the transaction. Participants then respond with their votes, either a commitment or an abort. Once all the votes are in, the coordinator makes a decision based on those responses. If everyone votes to commit, the transaction is finalized. But if even one participant votes to abort, the entire transaction is rolled back. While 2pc is fairly straightforward and ensures atomicity, it does have a significant drawback. If the coordinator fails after collecting the votes, but before announcing the decision, the participants are left in a state of limbo. This situation, often referred to as blocking atomic commitment, can severely impact system reliability and performance, since participants cannot proceed without the coordinator's final word. To tackle the limitations of 2pc, let's explore the three-phase commit protocol. 3pc introduces an additional phase to the process, which helps reduce the risk of blocking. After the coordinator collects the votes, it moves into a pre-commit phase before the final commit. This phase allows participants to prepare for the commit without actually finalizing it, creating a safety net for recovery if the coordinator happens to fail. In addition, 3pc incorporates timeouts. If participants don't receive a response from the coordinator within a certain time frame, they can make decisions independently. While this reduces the likelihood of blocking, it does come with increased message overhead and the potential for inconsistencies during network partitions. These trade-offs can limit the practical application of 3pc in certain environments. Now, let's enhance our understanding by looking at the Calvin protocol, which takes a different angle on managing distributed transactions. Calvin boosts transaction efficiency by establishing a deterministic execution order before any locks are acquired. This is achieved through a sequencer that oversees the order of transactions, allowing nodes to execute them without the need for extensive coordination. By determining the order of operations in advance, Calvin minimizes the overhead associated with coordination and enables nodes to recover from failures without needing to abort transactions. This efficiency is especially beneficial in high-throughput environments where cutting down on latency is crucial. Shifting gears, let's turn our attention to Google's Spanner, a sophisticated distributed database system that tackles the challenges of consistency and transaction order in a more complex way. Spanner supports three types of operations: read-write transactions, read-only transactions, and snapshot reads. Read-write transactions require locks and a leader replica for coordination, ensuring that writes are synchronized across the system. On the flip side, read-only transactions can be executed at any replica without locks, which provides greater flexibility and speed. Snapshot reads utilize versioned records with timestamps to deliver consistent data, allowing users to access the state of the database at a specific point in time. The architecture of Spanner includes span servers that manage tablets and employ Paxos groups for data placement and replication. Each Paxos group has a leader that oversees write operations and manages concurrency through a lock table. This structure not only ensures efficient data access, but also allows read operations to be performed directly from up-to-date replicas, significantly enhancing overall system performance. As we wrap up, it's clear that managing distributed transactions is a complex challenge that necessitates careful consideration of various protocols and strategies. We've examined the foundational two-phase commit and three-phase commit protocols, noting their strengths and weaknesses. We also explored the Calvin protocol, which enhances efficiency through deterministic execution, and Google's Spanner, which offers a sophisticated approach to consistency and transaction management. Each of these methods presents unique solutions to the challenges of distributed transactions, balancing simplicity, efficiency, and reliability. As systems continue to evolve, understanding these protocols will be essential for developers and engineers looking to build robust and scalable distributed applications. Thank you for joining us today, and we hope you found this exploration insightful. Be sure to stay tuned for our next episode, where we'll dive even deeper into the captivating world of distributed systems.